Welcome back to the Deep Dive. This is the show where we take the sources you provide, unpack them, and really get into the most compelling and essential insights without getting lost in all the noise. Today, we're diving deep into the world of light, specifically color and polarization. We're going to explore how we actually perceive, the vibrant world around us. Everything from the color of that shirt you might be wearing right now to the clever way your sunglasses cut through blinding glare. It really all hinges on this incredible, often invisible dance between light and matter.
Absolutely. And by the end of this deep dive, you'll gain a genuinely new perspective on stuff you see every day. We're talking about, why a green leaf can actually look black under red light, or how your television screen creates millions of colors from just 3 basic ones, and the hidden properties of light that your sunglasses use. It's really about looking at familiar things with, well, fresh eyes.
Okay, let's dive into color then. So when we look at objects, their color isn't some fixed property they just have. It's more like a dynamic interplay, right? Between the light hitting the object's own structure, and then how our eyes and brain interpret whatever light bounces off. That's why, a white wall reflects pretty much all light, while a black object seems to just absorb it.
Right, swallows it up.
And the green leaf example from the sources that really hits this point home. Under normal white light, like sunlight, a green leaf looks green. Why? Because its pigments reflect mostly green wavelengths. But here's the twist, and this is where it gets really interesting. If you shine only red light on that same green leaf, it suddenly appears black. What's going on there? That seems, almost counterintuitive.
Yeah, it does, doesn't it? And it's a perfect illustration. What's really illuminating about this is how color isn't just in the object itself. The leaf's pigments are basically set up to reflect green light. So when you only give it pure red light, well, there's just no green light there for it to reflect. And the red light that is shining on it, the leaf's chlorophyll pigments, they just absorb that red light.
I see.
So it really highlights that color is this conversation. It's a dynamic thing created between the light source, the object, and our perception. It's less about the leaf being green and more about it performing green when the right light is present.
That idea of light creating our perception of color,
Yeah.
that's fascinating. So if that's how single objects get their color, what happens when we start mixing colors? Because as the sources point out, there are 2 very different, almost opposite ways this happens. Let's start with additive primary colors. This one's all about mixing light itself. Think theater spotlights maybe, or the tiny lights in your phone screen. The primary colors for mixing light are red, green, and blue. And when you combine these RGB lights in different amounts,
You can make basically any color. You get the whole spectrum.
it's a pretty neat system. When you mix, say, red light and green light, you actually get yellow light.
Right. Not intuitive if you're thinking paint. Not at all. And then if you take that yellow light and combine it with blue light, the result is colorless, or what we perceive as white light. And because yellow, when added to the primary blue light, makes white light, we call yellow the complementary color of blue.
Okay.
And the sources mention this nice symmetry. Mix any 2 primary additive colors, and you get the complementary color of the 3rd primary. It's this balance that lets our brains build this rich visual world from just 3 light inputs. Pretty efficient.
So if additive colors are about mixing light, where do we actually see this happening in, everyday life?
Well, one place the sources mention is how chemicals give color to glass. Like iron compounds can make glass look green. Manganese compounds can make it look magenta, which is sort of a reddish blue.
Okay.
And here's the clever bit. Green and magenta are complementary colors. Add them together in the right way in the glass.
They cancel out.
They effectively cancel each other's color effect, yeah. The glass looks colorless. But probably the most common example, the one you see all the time, is your TV screen, or your computer monitor, or phone screen. Those screens are packed with millions of tiny red, green, and blue light emitters pixels. By tweaking the brightness of each RGB element in different spots.
They trick your brain.
Exactly. They trick your brain into seeing a full, vibrant picture with millions of apparent colors.
And that connects right back to our own biology, doesn't it? Our eyes are literally built for this. The sources remind us we have 3 kinds of color receptors, the cone cells, in our eyes. And guess what? They're sensitive to red, green, or blue light.
Yep. Our brain takes the mix of signals from those cones and interprets it as all the colors we see.
Okay, so that's adding colors using light. But then there's the other way, right? Mixing paints or inks or crayons, that's completely different. That brings us to subtractive primary colors.
Right. And this is where people often get tripped up because mixing yellow and blue light gives you white.
But yellow and blue paint gives you green. Everyone knows that from art class.
Exactly. So what's the deal? Well, the core difference is that pigments, like in paint, they don't add light. They work by filtering out or subtracting colors from the white light that hits them. They only reflect what's left over.
Subtracting out.
Let's use that source example. Mixing yellow and blue paint makes green. Here's why, basically. Yellow pigment absorbs or subtracts blue and violet light. It reflects the rest, red, orange, yellow, green.
Got it.
Blue pigment, on the other hand, it subtracts red, orange, and yellow light. It reflects green, blue, and violet.
So when you mix them,
The only color that both pigments reflect, the only one that isn't subtracted by either the yellow or the blue pigment, is green. Everything else gets absorbed by one or the other.
so what are the primary colors for this subtractive system? It's not red, green, blue anymore.
Now, for pigments, the primaries are cyan, magenta, and yellow.
Ah, like printer ink cartridges.
Precisely. Cyan, magenta, yellow. And here's a cool connection. These are the exact same colors that are complementary to the additive primaries we just talked about. Red's complement is cyan, green's is magenta, blue's is yellow.
Oh, that's neat. Okay, so what happens if you mix all three primary pigments together? Cyan, magenta, and yellow.
Well, if you mix them in the right amounts, they basically subtract all the colors from the incoming white light.
So you get black.
Black, or something close to it. All colors are absorbed, nothing significant is reflected.
And the sources add a little practical point here.
Right.
About why mixing paints in real life might not give perfect results.
Yeah, that's a good point. The blue or yellow pigments we actually use in paints aren't always, let's say, pure in how they absorb light. They often reflect a little bit of light from nearby colors in the spectrum, which means predicting the exact mix can be tricky unless you know precisely what wavelengths each specific pigment absorbs and reflects. It's not always clean textbook theory in practice.
Right, that makes sense. Okay, so we've covered color perception, additive mixing with light, subtractive mixing with pigments. But there's this whole other fascinating property of light mentioned, polarization. This is the secret sauce behind those fancy sunglasses, the ones that cut glare really well without just making everything dark.
Yeah.
So to get polarization, we first need to think about regular light, right? Unpolarized light, like from the sun or just a normal light bulb. The sources say its electric fields are oscillating kind of randomly in all directions, like a big jumble.
Exactly, a chaotic mess of vibrations. But you can think of all those random directions as basically combinations of waves vibrating vertically and waves vibrating horizontally.
Okay.
Now, linear polarization is when you somehow filter that mess down so you have a beam of light where all the electric field waves are lined up, oscillating in just one single direction. Nice and orderly.
So how do you get light to do that? How does it become polarized? The sources give us, what, three main ways. First up is transmission.
Right. Certain transparent crystals have this property. They act like a kind of filter. The analogy used is like sending a wave down a rope through a picket fence.
Yeah.
Only the parts of the wave vibrating up and down, parallel to the fence slats, can get through. The crystal has a similar structure at the molecular level that only lets light waves vibrating in one specific direction pass through. And that specific line, the direction the light can pass through and becomes aligned with, that's called the transmission axis.
Okay, the transmission axis.
And if light waves happen to be vibrating at, say, a 90-degree angle to that axis, perpendicular to it,
They get blocked.
they get blocked. They just won't pass through at all.
So if I had one of these polarizing filters, how could I actually tell if some light shining through it was polarized?
Oh, you could test it easily. You just need a second polarizing filter. You hold it up and look at the light source through both filters, and then you rotate one of them.
And what would I see?
You'd see the brightness change. When the transmission axes of both filters are lined up, parallel, the light will be brightest. As you rotate one, it gets dimmer. And when the two axes are perpendicular, at 90 degrees to each other.
No light gets through.
Exactly. The light becomes darkest, or might even seem to disappear completely. It's like you're tuning into this hidden property of the light.
Cool. Okay, so that's transmission. The next way is reflection. And this is the key for those glare-reducing sunglasses, right?
This is the big one for sunglasses, yeah. So when unpolarized light, like sunlight, bounces off a smooth, flat, non-metallic surface, think sunlight reflecting off a calm lake or a wet road or maybe the hood of a car.
Yeah, that blinding glare.
That glare. At certain angles, that reflected light becomes almost completely polarized, and crucially, it becomes polarized parallel to the surface it reflected from.
So flat surface like water or a road, the glare is polarized horizontally.
That's it. The glare you experience is mostly horizontally polarized light.
Okay, so those special sunglasses,
All right.
what are they doing?
They're designed very specifically. Polarizing sunglasses have their transmission axis oriented vertically.
Ah, vertically.
Vertically. So that horizontally polarized glare hits the vertical filter. The angle between the light's polarization and the filter's axis is 90 degrees.
So it gets blocked.
It gets blocked. Almost none of that specific glare-causing light makes it through to your eyes. But other light, vibrating in other directions or vertically, can still pass through.
That is clever. It filters out the annoying part without just dimming everything equally.
Exactly. It selectively removes the horizontally polarized glare.
Okay, and the third way light gets polarized is scattering.
Right. Scattering is basically when the light gets absorbed and then re-emitted by tiny particles, like the molecules in our atmosphere, nitrogen and oxygen molecules.
And that's why the sky is blue, isn't it? Something about scattering blue light more.
That's part of it, yeah. Blue light gets scattered more effectively by air molecules, but scattering also causes the sunlight to become polarized.
How does that work?
Well, when the unpolarized sunlight hits an air molecule, it makes the electrons in that molecule vibrate.
Okay.
Those vibrating electrons then re-emit light, but the light they re-emit in certain directions is polarized. So, get this. If you stand with your back to the sun on a clear day and look straight up, or maybe 90 degrees away from the sun,
Yeah.
the blue skylight you're seeing is actually significantly polarized. You could test it with a polarizing filter.
Huh. Never knew that. Okay, so we've covered a lot here. We've really taken a deep dive into color and polarization.
Yeah.
It seems like from the pigments in your clothes to the TV screen you're maybe watching this on to your sunglasses, light isn't just light. It's this really complex interaction of wavelengths and these oscillations.
Yeah, and it actively creates the visual world we experience.
Right. It makes you realize how much of what we think we see is actually just the light bouncing off things in particular ways, interpreted by our eyes and brain.
And this it's not just, textbook physics for exams. It really explains the why behind so many things. Why artists mix paints the way they do, how photographers use filters to manage reflections in their shots, how our own eyes work. It's about seeing the physics that's happening all around us, all the time, in the everyday stuff, turning the mundane into something kind of marvelous, really.
So the next time you pull on a brightly colored shirt, or you put on a pair of polarizing sunglasses, let me just pause for a second. Consider, what invisible properties of light are right there playing out, shaping the colors and the clarity that you're experiencing at that very moment.
Yeah, and here's a thought to leave you with. If objects that absorb all light appear black to us, what would a truly invisible object look like? Would it have to be black? Or would it be something else entirely? Something that neither reflects nor absorbs?
Lots to think about. Keep those questions coming, and definitely keep exploring.